Well, good afternoon, ladies and gentlemen. Today I want to discuss work that I've been doing over the past few weeks. Now, it's been about 3 weeks since I had this in mind. However, it took a while in order to manifest it and make it functional, since there's a lot of different nuance that I was not expecting. However, after deep analysis of all of its parts, I have now completed this functional system, which is quite wonderful. And so I want to express it to you so you can understand what this is. So I've called this system the Helioscopic Circular Ramp. This is the version 2.2, which is about the seventh or eighth different attempt that I've made of trying to realize this system. Now, why is this important? This is important because I'm trying to design a gear system that will be embedded into the arms of a pair of sunglasses. Now, why do I want to do that? Is because I want to create a high quality hinge mechanism that will create mechanical advantage as you move the arms, and it will create a sense of sturdiness and robustness. So that's my objective. Now, to do this, I am starting with this scaled up version that is 3D printable and functional. And so that is the result that I have for this gear system. Now, this is a planetary gear system that has two different levels and that has a total gear ratio of 3:1. Notice that I keep the mat very simple to 3:1 because I've tried a bunch of different prisms, and this is the most stable mathematical output that I had, so to negate all the complexities that come from using other types of prisms. So if I look around here, I actually used many different prisms. I had to come up with names to define them since they were so complex. So I'm gonna show them right here. So if I go here and I go this. So this one here is in the shape, it was inspired by the shape of the Pyramid of Giza with its concave sides. I thought that this might be one of the most effective prisms if I'm aiming for the end product to be as small as can be, perhaps a microscopic level gear system. I need to create it from the most basic shapes imaginable. That way I'll be able to reduce it to an extremely small size. So I started with this. I thought I'm going to start with the pyramid with a square base and then elongated points so that it is symmetric. Now, the important key to keep in mind in the design of the system is that I require to have a center of gravity or balance point for these prisms to be able to spin on a stable axis. If the mass is not centered in that prism, that means that the roll will not create even distribution of energy. It's going to be influenced by the mass of gravity of those objects, and so they have to be symmetric on the z-axis, going in opposite directions, so to create a balanced center of gravity in the middle. So this is the first shape. Then I thought maybe I should also try a few different shapes in order to see which one is the most effective. So I decided to name this an octospire because it is an octagonal shape, and it is based off of a concave square, and it creates 8 sides, and therefore I called it octospire. I also tried this with a radiant cut prism, which is the same as a gem that you would see on a ring. So this radiant cut here, which is a square shape, I tried to do this since the simplicity of its shape would perhaps give insight about how I can use the most simplistic prisms in order to represent their movement on a circular track. I've made some experience with those and with the octospire. However, I encountered an issue, and that issue is that the number 4, that's the 4 corners of those prisms, creates irregular pattern in the rotation, meaning that if I want to scale it down, the qualities of pi with its decimal points creates a problem when it comes to making the seam, and so it implies that there is an amount of slip that is necessary in order for the gear to create the right rotation, and the slip is the enemy of a gear system, and so I need to take that out. So after trying a few different things and thinking about it, I thought that I should remain myself to a hexagonal approach, since a hexagon, when you measure its circumference, is exactly 3 times the size of its diameter, meaning that It is easily divisible by factors of 3, and enables for this simplicity or simple output in terms of mathematics, and thereby I'm evading the inaccuracies caused by pi by using a hexagonal based prism. And so I tried with basic hexagonics first, which I call here the hex gem, so I'll show it to you. So I tried to make that system with this shape, which to me seems like a very effective prism to use. If I'm to create this on a microscopic scale, this is a shape that could be achieved. It has a center of balance and it has 6 sides. Now I would also like you to notice how this initial shape has the same amount of vertices as a cube. If I take out the beveling, the amount of vertices necessary to express the shape is the same as a cube. However, their position in space is quite different than a cube. So what I like about that is that it is one of the most simple shapes that can be created, and still maintain a large amount of efficacy in terms of using it into this system. So I thought this was the best way forward. So I made a few experiments with the hex gem, tried to make it part of the system, and I came up with a few results, and then I decided to refine the shape into something else, which is this one. I call that a dodecagem, which is a 12-sided gem. Since it does have the 12 sides, what I did is I used the hex gem and I indented, subdivided the initial plane and then indented it in the middle. This way would create this cavity. Now this cavity is very useful so to create the predictable gear behavior. Because I was using a flat side on the other one, I was scared that it would create a lack of adherence, meaning that the gem might not be able to lock with the teeth as well. And so I think that the cavity here is the optimized version of this setup. And so if I go back to the top view, I'm going to take the planets back up out, and I'm going to show the whole thing. Now what this system does is that it uses dynamic paint in order to record the movement of the prisms over time. And I use time here in order to register this imprint, and thereby I can create any shape or outline or tooth cavities in the circular track by inputting the right spin values for the numbers. Now because Blender is an animation software and it's not an engineering software, there's a big deviance between the reality of the measurements and the animation reality, meaning that I can set an amount of spin that is not representative of the of reality, and so it's quite difficult to figure out what is the right amount of spin for each part. However, it is possible to accomplish that mathematically so that you can get a stable output, and that's what I got right here. And now since this is done, then I show it. So I'm gonna show to you guys what this looks like. So let's go ahead. So you can see here that as the prisms rotate, they create an imprint on the different circular tracks. Now this is a 2-level gear, planetary gear system, where the inner gear, the sun gear, which is over here, will spin 3 times for every 1 rotation of the outer gear. And so the translation is handled by these prisms here that serves as the planetary gears. Now you can see here that this creates a very stable pattern, and that the shape of the prisms is being recorded by this system. Now here I've got I got 4 different canvases set up like this, and I got 9 prisms. So it took a while to figure out all the right math and proportions for it. But you can see how stable the pattern is now. It's returning to its origin. There is no overlapping or phasing of the cavities that is being made. That is because of the shapes that I'm using. They created easily divisible by 3 format, meaning that 120 degree rotation is really enough to record all of the action. Now I did set it to do 2 complete rotations, because if the prisms are not hexagonal, or if I'm using another shape, the second rotation might show some phasing where the teeth do not track with the first spin, and so that's why I set 2 rotations for it. And so now you can see that the tracks have been imprinted with the shapes of the gears. And at the end of the animation, which is 500 frame, I'll be able to use a series of operation in order to translate this into a printable geometry. So I'm just going to let this finish here, 480. Okay, so let's go to 500. Alright, so you can see here that the gears have been imprinted with the right cavity shapes, so to accommodate the movement of the object. You can also see that the prisms are engaging at every point so that it creates a stable structure. So once this system is made, so you can see here that it enables me to record any object. I can use any shape of prism. It could be a cylinder, it could be a cylinder with a teardrop point, it could be an oval shape, it could be anything. And there's many different other tests that I wish to make, especially with the oval motion. I think the oval nature and teardrop motions, alongside with nautilus shell objects, would be very interesting in what they could do, and this method would enable me to record any shape of prism. So I think that's what is so masterful about this, is that it enables me to create this scientific method with any prism, and then get at the end a result where I can print that gear system, which is quite amazing. So I'm gonna erase those plans here, and the tracks, or hide them, and then I'm gonna go back to the export geometry, which is here. So you can see here that I've basically used the same geometry, and I've related and breached the edge loops. Now there's a few different magic tricks that I had to do in order to get there, and I'm gonna keep the secret for myself because I can't reveal all the tricks. It would be bad for practice, I guess, but I'm sure you can figure it out. So I did a bunch of different magic tricks in order to realize this as a mesh, and now you can see that those parts are all individually printable, and also I did add the right clearances so that they can print without issue. So if I go into the printing file here, you can see it right here. And you can see that the cavity is quite tight. I do not want to have large tolerances. I want the tolerances to be quite tight, but I also want to make sure that they don't print as being the same part so that they can move freely in the system. Now you can also see that the way the cavities were imprinted in the system, it creates this conic cavity shape instead of having a straight or flat two-dimensional gear approach. And that's a big difference, because a two-dimensional approach to gear system means that there's going to be lateral forces that can apply, and so the gear can slide out of place. It's not going to be stable. Now the way that I made this, because of the shape of the prisms, it means that the channel for the prisms is conical from the side or front view, meaning that the prisms cannot escape the cavity, and it will be self-centering because of the mirrored z-axis. So that's really interesting. The other thing that I think is really cool about this is that when you look at it printed like that, this looks like a religious symbol, which is quite odd. To me, it's like religion has figured out a bunch of things that science did not figure out yet, and so they put it into symbols and other stories. But then when you start to crack the nut in terms of science, you start to realize that these things make a mathematical sense, and so they are represented into religious mean. I find this relationship to be quite interesting. Anyway, so you can see how the geometry here is quite perfect. It's super centered, super balanced. There is no offset or anything. It is printable like this. So this should be printed in about 40 minutes or so. I'll be able to try it right afterwards. Now I do intend to have multiple stages of this, so this would be first layer, but well, there's 2 levels here, but then I could put multiple stacks of those and achieve multiplication of 3 every time. So I'm thinking maybe 12 as the output. 1 to 12 would be a good setup, and because of the way this is made, I'm thinking I can print it so that the outer circle is of a diameter of maybe 5 millimeters. For the outer circle, but I would need to check that because that's not simple to do. But it might be possible to print this using lasers to make it happen. I still have to consider about what to do with it. But this being said, there's so many different things that I can do with this. The helioscopic ramp, if I go back to this thing, so this is a circular format for the helioscopic ramp, but the truth is this idea is much greater than just a circle. It can be applied to flat planes. It can be applied in order to translate any shape into a specific type of normal maps. that will enable to transfer the shape of the prism to any flat surface in a displacement modifier, meaning that I can take any shape and create the path from that shape that will enable it to roll smoothly. And why is that important? Well, it's important because if you want to create organic motion in mechanical systems, you cannot consider only bearings or only flat or two-dimensional gears. If you want to have a robot that moves in an organic fashion, the consideration about the way the gear systems are created will have a major impact on the natural or organic qualities of the movement that is produced. Meaning that if I use a Nautilus shaped gear in order to create multiple different movements, or it doesn't have to be a gear, it can also be just a Nautilus shaped prism, then I can create a variety of predictable movement through its analysis in this method, where I can have it roll in one direction and then turn as a result of a track that is specifically made to do that. And this setup enables me to create such predictable movement. So this resumes the work that I've been doing outside of the music for the past maybe 2 or 3 weeks. I think this is a beautiful step forward, and I wanted to share it with you guys. So thanks for your attention, and I'll see you soon.